So in our last video, we introduced the concept of a dimension of a vector space. Remember, a dimension of a vector space is basically the size of any basis. The size of any basis for a vector space. We said all bases have to have the same size. So I want to kind of blend 4.5 together with 4.6. They flow together naturally, so I'm just going to kind of flow into 4.6. We're kind of dealing with 4.5, the end of it, 4.6 flowing together. 4.6 is about something called rank. Let's go ahead and define rank. It's not defined in 4.5, but it actually shows up in 4.5. They don't define it yet. So definition, just write def for short. Let A be an m by n matrix. The rank of A is what we're defining. I'll underline that. The way you denote the rank is rank parentheses of A is the dimension of the column space. The dimension of the column space of A. So in other words, that is rank of A. Well, it didn't come out right to it. There we go. Is rank of A is defined to be equal to the dimension of the col of A, the column space of A, of course. Okay, so here's an important theorem about the rank of A. Rank of A equals the number of pivot columns. If we wanted to prove that, we could prove that real quick. I'm not even going to bother proving it. I'll just talk through the proof. So remember what the rank is. The rank is the dimension of the column space, right? The dimension of the column space. Think about the column space. How do you get a basis for the column space? Remember we said to get a basis of a column space, you look at the pivot columns of the original matrix A. So the original pivot columns of A will give you a basis. So however many pivot columns you have, that's going to be the number of vectors you're going to have in your basis. So that's going to be the dimension of the column space. And what's the dimension of the column space? It's the rank. So the rank is just the number of pivot columns of A. So you can talk your way through the proof, or you can write it out. I'm not going to bother writing that one out. So rank of A is just the number of pivot columns of A. Here's another definition. We're going to talk about something called the nullity. Let A be an m by n matrix, be an m by n matrix. The nullity of A that's denoted nullity parentheses of A. That's the dimension of the null space of A. The dimension of the null space of A. Let's see. Okay, so in summary, that is to say that the nullity of A is defined to be equal to the dimension of the null space of A, null A, dimension of null A. So remember what the dimension of the null space of A, that's just the number of vectors and a basis for the null space of A. Now this one is not so easy to prove. It's not too hard to prove. I'm not going to bother proving it. So here's a theorem about the nullity of A. Nullity of A equals the number of non-pivot columns, the number of non-pivot columns. Yeah, so that's really not hard to prove. So I mean, kind of talk your way through it. So when you're thinking about the nullity of A, it's the dimension of the null space. So think about what is the null space. The null space consists of all solutions to the homogeneous linear system, or the homogeneous matrix vector equation. So the number of vectors that are going to form a basis in your null space, that's just going to depend on the number of free variables. The number of free variables. So the number of non-pivot columns determine the number of free variables. So yeah, free variables correspond to non-pivot columns. And that's what's going to give you your basis for your null space. So the number of basis vectors is your nullity. So yeah, the number of non-pivot columns of A is the nullity of A. All right, simple enough. So pivot columns is rank, non-pivot columns is nullity, you can say, for short. It's kind of a simplification. All right, so what are we ready to do? Example. Let's do an example. Find the rank of A, which is sometimes called the dimension of the column space, and nullity of A, which is sometimes called the dimension of the null space of A. Find the rank and the nullity. Okay, number one, here's my matrix, capital A, 2, 0, 0, 0, 1, 1, 0, 0, 3, 0, 0, 0, 5, 4, 0, 0, 7, 2, 5, 0. So I want to find the rank of this matrix. So to find the rank, also known as the dimension of the column space, I'm just going to look at the pivot columns. So columns 1, 2, and 5. So we have rank of 3, right? 3 pivot columns. As for our non-pivot columns, they would be what? 3 and 4. So the nullity of A, that's your number of non-pivot columns. That's going to be 2. Rank is 3, nullity is 2. All right, easy enough, right? Pretty easy stuff. Number 2. So you got A is 5, negative 25, negative 3/5, and 3. So what you need to do is row reduce this to see which columns are pivot columns. So I can multiply the first row by 5, right, and add it to the second row, and I'll get 5, negative 3/5. See, 0, 0. And if I multiply the first row by 5, I'm going to get, what, 25 minus 3. If I add 25 and negative 3 to negative 25 and 3, I get 0, 0. We can see very clearly that we have a pivot here in the first column, and that's it. So our rank of this 2 by 2 matrix is going to be 1. And as for the nullity, we have one free variable, right, x2, or I should say we have one non-pivot column. So the nullity of A is 1. One pivot column, one non-pivot column. That's simple. Rank and nullity. All right. So a really big result. So I'm like fully now in section 4.6. Really big result that shows up. And this theory of linear algebra is called the rank plus the nullity theorem. So our book calls it the rank theorem. I'm going to call it the rank plus nullity. So let's say you have an m by n matrix. If A is an m by n matrix, then the rank of A plus the nullity of A, you have to add up to n. Think about that for a second. So what is rank? Rank is the number of pivot columns. What is nullity? Non-pivot columns, they have to add up to what? The total number of columns, n, right? They have to add up to the total number of columns. So pivot columns plus non-pivot columns adds up to the total number of columns. So if you have an n by n matrix, rank plus the nullity is n, the number of columns. Big deal. And I mean, you can observe that previously, right? We had rank 1 and nullity 1 that had to add up to 2 because there are 2 columns. In the previous example, we had rank 3, nullity 2. They had to add up to 5 because there are 5 columns in total. Just common sense. All right, here's another important theorem. So I'm going to call this bounds on rank. Bounds on rank. So what is the rank bounded by, above and below? That's the name I'm going to give this theorem. I think this one's in your book, but it's important. If A is an n by n matrix, then the rank is in between, rank of A is in between 2 things. First of all, the rank must always be at least 0, right? Doesn't make sense to have a negative rank. I mean, at the least you can have is no pivot columns, right? If you have 0 pivot columns, that's one worst case scenario for the rank. But the best case scenario for the rank, what's a maximum value you can put on the rank? So the number of pivot columns is limited by the number of rows and by the number of columns. So you have to take those 2 things into account. So the number of pivot columns is both limited by the number of rows and columns. So it's the minimum of the number of rows and columns. So that's an upper bound. So a lower bound is 0 on the rank, and an upper bound is the minimum of the number of rows and columns. Yeah. So for example, let's do a quick example here. If I had a 3 by 5 matrix, 3 by 5, 1, 0, 0, 0, 1, 0, 0, 0, 1. I'm limited by the number of rows I have here, right? I can't have any more pivot columns, right? The most I can have is 3 here. That's the most number of pivot columns I can have. So I can add extra columns, right? I have a 3 by 5 matrix. I can put stuff in here, 5, 6, 7, 8, 9, 10. But I'm limited by the number of rows here. So the number of rows limits me to the number of pivot columns. So the maximum number of pivots I can have here is 3 because I have a 3 by 5. Yeah. So you have to take into account this, the minimum of the m and the n. So 3 is smaller than 5, so we could only have at most 3 pivots. Okay. That's important. What about bounds for nullity theorem? Bounds on the nullity. I don't think this is in your book either. I don't know why they don't put this stuff in the book. I guess they assume it's common sense. I don't know. This is an important result. If A is an n by n matrix, is an m by n matrix, then the nullity is bounded above by, think about it for a second, what's the most number of non-pivot columns you could have? You could have, all of them could be non-pivots, right? If you had like just columns full of zeros, columns full of all zeros, at most you could have n columns that are non-pivot. And the least you could have, I'm going to tell you the answer to this, is n minus the minimum of m and n. Let me see if I can fit this in here. Minimum of m and n. So I mean, the upper bound is obvious, right? At most, you can have n non-pivot columns. Let's actually show why. Do a partial proof for the lower bound. Lower bound. So what do we know? We know what? Rank, that's the number of pivot columns, plus nullity, that's the number of non-pivot columns, has to add up to the total number of pivot columns, n. Okay, what else do we know? Let me put the n on the other side. It would be beneficial to have the n on the other side of the equation. Let's put the n over here. What else do we know? Well, we know the rank here has an upper bound, right? Rank has an upper bound, so this is going to be less than or equal to the minimum of m and n, right? The rank is limited by the number of rows and columns. And then we got plus the nullity there on the end, plus the nullity. So what do I have? I have n is less than or equal to the minimum, right, of m and n plus the nullity of a. So what I can do now, I can subtract the minimum of m and n from both sides. I get n minus the minimum of m and n is bounded above by the nullity of a. Or that's a lower bound for the nullity of a, I can say. That's another way to say that. It's a lower bound. So that's a partial proof there. Yeah, good enough. So it's important. So your nullity has to be at least n minus the minimum of the number of rows and columns. So that's useful. Let's see. Let's do some exercises. Give an example. Give an example of a matrix with the following properties. With the following properties. Yeah, it didn't write too well, did it? Following. Number one. Oh, if not possible, say why. If not possible. Let's say you can't come up with such a matrix. Give a reason. All right, number one. Let's say we want a 4 by 4 matrix. A is a 4 by 3 matrix. And the rank of A should be 2. So all you have to do is come up with a matrix. We're going to call it A. It needs to have 4 rows, 3 columns, and it has 2 pivot columns. So we're going to do what? 1, 0, 0, 0, 0, 1, 0, 0. And just, so we already have our 2 pivot columns, right? We want to make sure we have 2 pivot columns because the rank is 2. And we just need to add an extra column to make sure it's 4 by 3, right? We have to have 3 columns, 4 rows and 3 columns. So 1, 2, 3, 4, 0. So that'll do it. You wanted a rank of 2. That's it. All right, how about another matrix? Another challenge set before us. Can we do what I have here? Challenge is A is a 3 by 5. And we want the nullity, that's the number of non-pivot columns. Nullity wants to be 4. Can it be 4? Okay, so tricky. You got to pick a 3 by 5 matrix. So you want what? 3 rows and 5 columns. And you want 4 of those columns to be non-pivot columns. So if 4 of those columns are non-pivot columns, that means one of the columns, right? So the rank here is going to be 1. Why is the rank 1? Because when you take 1 plus 4, it has to add up to the total number of columns, right? 1 plus 4 has to give you 5. So we're just looking for a 1 pivot column situation, right? 1, 0, 0, right? We need 3 entries going down because it's a 3 by 5. And then you just have to come up with 4 non-pivot columns. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Here are our 4 non-pivot columns. Now, we didn't have to put zeros up there at the top. If we wanted to, we could have put something else in. We could have put in like a 9 there, right, if we wanted to. But I'm just going to put zeros. It's an easy thing to do. All right, so that's an example right there. Right, nullity 4. You have 4, 1, 2, 3, 4 non-pivot columns. It's a 3 by 5 matrix. Okay, let's see. What else can we do? Number 3. A is a 4 by 8 matrix, and the rank of A, we want the rank of A to be 5 if possible. Well, it turns out this is impossible. This is impossible. Impossible. And the reason that it's impossible is because the rank is bounded above by 4, right? You take the minimum of 4 and 8, and that's the maximum. That's the maximum number of pivots, right? Maximum number of pivots. So note the rank of A has a maximum of, that's a bound above by the minimum, the maximum is the minimum of 4 and 8. Right? You're restricted by your number of rows and columns that you have. So the smaller of the two numbers. So that's the rank. A is less than or equal to, what's the minimum of 4 and 8? 4, right? So rank is less than or equal to 4. So it's impossible to have a rank of 5. All right. Let's do a number 3. What's number 3? That was number 3. Let's do number 4. How about, can we find a matrix A? A is a 3 by 7 matrix. And the nullity is 2. Let's see, can we do that? So you want a 3-row, 7-column matrix with 2 non-pivot columns. So that would mean you would have to have 5 pivot columns, right? The rank would have to be 5. Why would the rank have to be 5? Well, if you think about 5 plus 2 would have to add up to give you 7. So it's not possible to have that situation. So it's impossible. One way to do this, you could say, well, the rank is at most 3, so it's impossible to have a rank of 5. But let's not even talk about a rank. Let's pretend we didn't know what the rank was. So what do we know? We know the nullity of A is going to be greater than or equal to n, right, which is 7, minus the minimum of m and n, 3 and 7. That was like a lower bound, right? We talked about earlier in one of our results. Where was that? Right here, right? Nullity of A is greater than or equal to n minus minimum of m and n. That's what we're doing here, right? Nullity is greater than or equal to that. So that means the nullity of A, that's funny. Didn't put an A in there, did I? Funny stuff, come on. Is at least 7 minus, and the minimum of 3 is 7 is 3. So nullity has to be at least 4. So since nullity is requested to be smaller than 4, right? Nullity has to be at least 4. That can't happen. All right, so I think we'll just quit right there, and maybe we'll pick up a little bit later.